So this tells us that Dan knows 50% of the time a phone battery lasts at least 19 hours, that's 19 or more. 25% of the time it runs out in under 14 hours, and it's distributed normally. So first step, we could define it, which is we don't know the mean or the standard deviation. So let's call it time the battery lasts is distributed normally. So I'll use T. I can use any letter I want, but T works. Distributed normally. Mean we don't know, we'll call it mu. Standard deviation and variance we don't know, so we'll call that sigma squared for the standard deviation for the variance. So that's defined it as being normally distributed as it says in the question. Let's draw a nice little Gaussian curve. There's our Gaussian curve. Here we have the mean. Here we have one standard deviation away. Here we have one standard deviation this way. It should be the same each side. It's symmetrical. We don't know where they are. But given that 15% of the time a phone battery lasts at least 19 hours, so if I put my values of T on here, at least I want 15% is going to be over 19. Well, 15% is definitely less than all this. So it's going to be around here somewhere. Let's put a line there and call that 19. And we know that this area here is our 15%, so 0.15. And then we know that 25% of the time it runs out in under 14 hours. So 14 hours. If it's 25%, that's quite a bit more than this, because this is 70%, so about there. So you have to one here that's about 14 in terms of T. And this must be, this area here, must be 0.25. That's our probability of it running out in under 14 hours. So here's our time here along this axis. And now it says, find the mean and standard deviation. Well, I don't know it. I can't use my calculator with the mean and standard deviation because I don't know it. I want to do an inverse normal, so the only thing to do is say, let's use our standard distribution, where Z equals whatever our variable is, in this case T, subtract the mean divided by the standard deviation. That's how I convert from T's to Z. So let's put Z in here. If it were a Z distribution, by definition, Z distribution, this is 0, the mean is 0, and one standard deviation away is 1, so that must be 1. That must be -1 and 1 to get to this point here and this point here. I don't know where they are in this distribution. We've got to work that out. So let's work out, at least in this standard deviation, in our Z distribution, I should be able to work out where this point here is here by the inverse normal with mean of 0 and standard deviation of 1, with 0.25 as my area, should give me what this value here is. So let's put that in the calculator as an inverse normal. I'll add a calculator page first, and then we need to find inverse standard normal distribution. So menu, statistics or probability, doesn't matter, distributions, and I want inverse normal number 3 there. And the area we want, first of all, is 15%, it lasts 19 hours. So we want 85% on the left hand side, so 0.85. That's our 15% on the right, it gives us 85% on the left. We want our mean to be 0 and standard deviation to be 1 because this is our Z distribution. Enter that, and there's my answer. And we find that we should get, actually I can't fit in here, it's too big to fit in, negative 0.674489, etc. And we do the same with the inverse normal of this one with mean of 0, standard deviation of 1, so that's 1, and put in an area of 0.15 for an inverse normal distribution. We can do similar, and first of all I should store that in a memory. I want that to be, let's store it in, oh no, I don't need to store it in memory, we can do that later. I'll do a inverse normal distribution for the other one, menu, 5 probability, 5 distributions, inverse normal number 3. Area is 0.25 because now it's to the left, which always wants areas to the left. Mean and standard deviation are both 0 and 1. And there's my equivalent of being 25% on the left, or 25th percentile. So that's those equivalents are 14 and 19 when we do our Z transformation, and now we need to put our simultaneous equations in. And the value in here gives me 1.036433, etc. You might want to store those in a memory so we can use them later, they may be useful. And now we know that this value here in Z is the same as this value here in T. And we've got a relationship linking Z and T. So let's put the Z value where the Z is and the T value where the T is, and those should match up in the equation. Negative 0.674489 dot dot dot. I hope I'll put it in the memory so we can use this in the calculator. Equals 14 subtract mu over sigma. We'll just replace this and this with the Z and the T values because we know they're in the same place. They relate to the same points on the curve on the Gaussian distribution. And we can do the same for the other values. We know that 1.036433 dot 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 is equal to 19 subtract mu over sigma. That's from these values here. Put them in for the Z and the T values. That gives me two equations. I can try solving linear equations, except they're not linear because I've got a mu divided by a sigma with sigma on the denominator. They're not linear, so I can't put them in. So let's multiply both sides of both equations by sigma to get 0.674489 dot 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 sigma equals 14 subtract mu, and 1.036433 dot 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 sigma equals 19 subtract mu. They're now linear. And on the nspire, you can put those into the calculator as two linear equations. I might use this as S and this as M, S and M for sigma and mu. Just so I know what the values are, you can use X and Y if you want. Just put this as an X and this is a Y, this is an X and this is a Y, as long as you're consistent across both and remember which way around they go. In the TI-84s, we've got to do another manipulation because the TI-84s, you've got to have so many X plus so many Y, or so many X subtract so many Y equals a number. So we have to add a mu to both sides so that it's on the other side. So we'll get mu subtract 0.674489 sigma equals 14. And on this one, mu plus 1.036433 sigma equals 19. I can put this in here now with this is 1x, and this is negative, whatever that value is in my memory, y. With a subtract there, and another side up of 14, and the second equation is 1 mu, then this value here, which is your value we got from here in a memory somewhere, and this in here too. And again, I'll be using memories on the nspire too in the same way. Menu, algebra, solve system of linear equations. Number of equations I've got is 2. I'll use the variables M for mu and S for sigma, so I know what they are. And now it sets up my two equations for me, which I'm going to do as mu is M, subtract or plus. So I need to go and take M plus and then go and copy that in. So I'll do Control C to copy it to get it in the right place in the equation. Control V to paste it in. And that is multiplied by sigma. So that's S equals 14. And the second equation is M, so mu plus this value here, Control copy, Control C, and put it in there, Control V, equals, sigma equals 19. There's my two equations. And it gives my two values there for M and S. So this is my mean, and this is my sigma. It's useful to store those somewhere, so I'll call them mean colon equals as a definition of error. So control the symbol just here. And then I'll go and still this value here. Unfortunately, it's hidden inside here a bit. So this is my mean. Hold the shift key down and go right. Hold the shift key down. Go right. Whoops. I'll have to copy it on here. It's normally hold shift D down. Go right. It will select it. Control C for the copy. And then come down to here and paste it. Control V. That's now defined. Oops. Missing. I'll do mean Z, because it's Z distributions. It doesn't like mean, that's the defined one. And I need sigma. Which is in italic, so it is going to accept it as a variable. It's not a defined, predefined thing it expects. And here again now to go to the right place, shift, go left or right, or go right, select that, control C to copy, bring that down into here. That's defined my sigma, so I can use those later on. Put those in, and your calculator will solve that equation for you and give you that mu equals 15.971128. which is approximately equal to 16.0 to 3 significant figures. Because the question asks for this mean, I can quote it to 3 significant figures. I will store this in my memory just in case I need it later. I can't use this in a subsequent calculation. I have to use this. The same goes for the sigma, which comes out as 2.92238989, or approximately 2.92 to 3 significant figures. And I just checked to see if this value of 16 looks reasonable. 16 in here, between the 14 and 19, the 14 is closer, which it should be, than the 19 is. That looks right. And 2.92 is about 3, so from 16 we're down to about 13 there, and from 16 we're up to about 19 here. So actually that's not just below 19, which this is supposed to be a bit further. So I've not drawn the diagram most accurately, but it looks reasonable in terms of my diagram there. Now watch out for this next question. This is one of the nice trick questions they love. She gets on the train one evening 17 hours after having charged the battery while it still has charge left. So we know before we start that she still had battery 17 hours after she left. Find the probability it will have battery left when she gets home an hour later. Let's look at what that looks like on the diagram. It means that on our nice Gaussian curve, like this, we've got 17 here and 18 here. And what we know is she was definitely up in this section. She definitely had 17 hours left because she still had charge left 17 hours later. And then we need to find 18 hours left. What's the probability of her getting in here, given that she had at least 17 hours left? And this is a given question. That is true. Find when that's true, given that this is true. It doesn't say the word given in there, so it's a bit confusing. And that means the probability that the time is greater than 18, so I end up with at least 18 hours left, still charged after 18 hours, given that she still had battery when it was 17 hours left, given that t was greater than 17. And in the formula booklet, one probability given another gives me the probability of the intersection, t is greater than 18, intersects t is greater than 17, over the probability of the one that's given, t greater than 17. On a Venn diagram, we can see it. Well, it's harder to see it here, but look carefully. This is exactly like a Venn diagram now. This is everything can happen. It's our rectangle. That's our greater than 17. That's our greater than 18 here. So now, where is the intersection of 18 and 17? Is where 17 is true and 18 is true, where we've hatched it both ways. That's our intersection. So here is the intersection, which actually is just the probability it's greater than 18. It's the same thing because it goes on forever that way. So we have the probability that t is greater than 18 is the same as the intersection, because greater than 18 is the same as the intersection of this and this, divided by the probability that t is greater than 17. So now I need to use normal distribution on my calculator, find the probability of t being greater than 18. So that's a normal CDF. My lower bound is 17, and my mean is here, and my standard deviation is here, not the rounded versions, the original versions. So make sure that's stored in the memory so you can put it somewhere. Be careful, you can't necessarily store it. You can use the X and the Y's on TI-84 to store it. On the Inspires, do a copy and paste, Control C, Control V to copy it out from an earlier part of your calculation into the new memory. If you can put memory name, I might put mu equals, and then copy and paste that in afterwards. I'll do the same for sigma equals, go and copy that from up further up and put it in. You have to select it with your shift to select a whole section, then Control V. And you could do Control V afterwards to paste it in. Now we've got the probability that t is greater than 18 or greater than or equal to 18. So now we need to use our menu distributions, just probability distributions. We want our normal CDF. And the lower bound now is so we want greater than 18. Let's do 18 first. So 18 up to 9 EE 999. Mean now is our, so we can go right here and select our Z mean, and then tab down, go right here and select our sigma, and then that will give us our value, our probability of being greater than 18. And we could do the same now. I don't want to bother going all the way through, so just click up here and press enter or copy it down. I want to change this value here to 17. And there's my probability of being greater than 17. And then for the final probability, we want to do a fraction. On top of the fraction, we want the greater or equal to 18. Given that it's greater or equal to 17, this is more hard done to copy that, Control C, because otherwise it will try and put it on the top of the fraction, Control V. And this gives me, when I work those two out, probability that t is greater than 18 is 0.362395. Sorry, 45, I think. Just check on my calculator. T is greater than 18. Uh, 0.362395. That's right. Divided by 0. Greater than 17, 243,763. And that gives me 0.67264, etc., which rounds to 0.673 to 3 significant figures. So this is the given probability to look for. If a phone has lasted at least 17 hours, which is what it says, so it's still working after 17 hours, the probability it lasts 18 hours is over 2/3. So if she doesn't have battery left after 17 hours, well, it's not going to last 18. We don't care about that. We don't care about anything down here. That's excluded from our calculation. Watch for those given ones. Now the next bit is, what's the probability that over 5 working days the battery lasts at least 18 hours? Well, it's lucky we worked out the probability of it lasting at least 18 hours here. It doesn't say given that in any place. So over 5 working days the battery lasts at least 18 hours exactly once. This is binomial distribution. Let's define our binomial distribution. I'll say the battery is good, so it lasts 18 hours, is distributed binomially 5 occasions with a probability of 0. Probability greater than 18. That's right. Probability is greater than 18 is 0.362395. That's not good. I've written these two probabilities the wrong way around. Back here, this should have been, this should have been the other way up. 0. Greater than 18, 0.243763 over 0.362395. That's better. it the right way in my calculator to put the answer out, wrote the wrong thing down. Okay, so now this is 0.243763, and when I put it into my calculator, I need to store this value in my memory. I calculated it when I did this section, so it's that value there. Put it into a variable so you can add it easily into your binomial distribution. Now we need a binomial distribution, the probability that we get exactly once, that it lasts 18 hours over 5 working days, so 5 events, probability that G equals 1. And we do a PDF for that because it's a single value. I just want a PDF if we look at, and we're looking at it lasts, we've got 0, 1, 2, 3, 4, 5. Here are my values. We want it to be exactly equal to 1. I think those are the wrong probabilities, but it gives me an idea of what I'm looking at. Binomial distribution. Binomial distribution, we need to have the probability that it is greater or equal to 18. So I want this probability here. Let's do probability 18. So I know what it is. Control it colon equals, and now go and take this value, which is what we want for that one. That's set up as a variable, and so now I can use it in my binomial distribution calculation. Menu, probability, distributions, binomial. We want a PDF first to be equal to 1, so that's A. Number of trials is 5. Probability of success. Go and pick up my probability of 18. We got X value of what to be once, and enter that. Gives the probability of getting it 1 time out of the 5. Probability G equals 1 gives me 0.398629, which is approximately equal to 0.399 to 3 significant figures. Now the probability that G is, it says, fewer than 2 times, so less than 2. Less than 2 is actually this. So I actually want the probability that G is less than or equal to 1. Watch out, it's now discrete, so I can't use actual values. Gives me less than 2 is now a CDF, so menu 5, 5, CDF is B. Number of trials is 5. Probability of success is the same as we had before, which is our probability of 18. Lower bound is 0, upper bound is 1. And there's a probability for that one. 0.645966. This is CDF. We now need to do this, which is approximately equal to 0.646 to 3 significant figures. And then greater than 2 times, more than 2 times is over here. So the probability that G is greater than 2 equals the probability that G is greater than or equal to 3. So actually on the TI-84s you need to do the probability, well we know it's probability of 1 for everything. Find the probability it's 2 or fewer, so go up to 2 and subtract that from 1 to get this side. On the TI-inspires you just do between 3 and 5 because the most we can have is 5 because it's 5 days. Probability that it is greater than 2, I can just copy this value and change that from 2, so greater than 2, so 3, 2, and at most we can have is 5. And there's a probability that's greater than 2. It gives us 0.09704727, which is approximately equal to 0.0970 to 3 significant figures. Make sure you put the 0 on the end because that's one of your significant figures.